Hey guys, so my name's Jono. I've also got Angus and Isaiah helping out today as well, and there's also some of the other execs in the group as well, floating around and helping out. So today we're going to be doing dynamic programming, and a lot of you probably would have already encountered some sort of dynamic programming, whether it be I think you do a bit of dynamic programming in Comp 3121, the algorithms course. And you might have touched on some of the basic stuff like recursion in Comp 1511 or Comp 2511. So today we're sort of going to be looking at dynamic programming in the context of programming contests, which means we're actually going to be implementing the algorithms that we're going to be coming up with. So in Comp 3121, you don't really implement any of the algorithms. You sort of just write out the algorithm in maths words or in plain English, but you don't actually get to implement the code for that and actually solve problems. So that's what we're going to be sort of focusing on today as well. And you'll see that there is going to be a bit of a difference, or there are going to be sort of things you need to keep in mind when you're doing the actual implementation, which slightly differs from the actual just writing it out on paper sort of thing that you do in Comp 3121. Also, this probably would be good revision as well if you're doing, if you haven't done algorithms yet. Okay, so, how do I go into the next slide? I think I need a mouse. Okay, so that's the sort of, let me move this out of the way. So that's the sort of table of contents, the sort of content we're going to be covering today. So first, we'll just do a bit of a background and a reminder of what dynamic programming is, as well as having a step-by-step guide for dynamic programming, which will just make sure that we don't really miss anything, or we have all the sort of steps. And then we'll cover 3 dynamic programming problems, including coding it up. And we'll look at different styles. So we'll look at bottom-up and top-down DP. And then at the end, if we have time, we'll look at some common DP patterns, which sort of might help you out if you're looking at sort of questions which follow the same sort of similar sort of theme, because you notice that a lot of problems will follow some sort of similar theme with your DP. So just first of all, a bit of a background, a quick refresher on recursion. So in Comp 1511 or maybe 2511, you might remember a bit about recursion. So the classic sort of question they would give you is you want to calculate the nth Fibonacci number. So write a program which prints out the nth Fibonacci number. And the way we define this is you have these 2 base cases. So f0 is equal to 1 and f1 is 1. So the first 2 terms are equal to 1. And then every other term, so f2 and onwards, is defined recursively as being the sum of the previous 2 terms. So this is an example of a recursive sort of formula, because each subsequent term is defined in terms of the previous terms. And the main idea here is with recursion, you're constructing larger Fibonacci numbers, so fn, by adding up your smaller Fibonacci numbers, fn minus 1, fn minus 2. So I'm sure you are all familiar with Fibonacci. And that's the main idea of recursion. And dynamic programming is an extension of recursion. So you're using recursion, but they aren't necessarily the same thing. Yeah. So I think a lot of students, they think dynamic programming and recursion are the same thing. I think on one of the slides in the courses, they say that dynamic programming is like smart recursion, or it's using recursion in smart ways, as well as having some sort of smart order of how you do that recursion, as well as some other stuff. In contrast to, there's also another similar technique called divide and conquer, which also uses recursion, but divide and conquer is a little bit different from dynamic programming, but they're still sort of similar concepts. So the main thing I just wanted to touch on here is just a reminder of what recursion is. So what is dynamic programming then? So it's a technique for solving complicated problems by breaking it down into many simpler subproblems. So if we've got, so later on we'll see these problems, and then we can break it down into smaller subproblems, and then we can solve these subproblems instead, and then we can construct our solutions for the more complicated problems by combining our subproblems together. So that's similar to what we did here with the Fibonacci sequence, where if we want to find Fn, we can break it down into two subproblems of finding Fn minus 1 and Fn minus 2. And then once we solve these two subproblems, we can combine those answers together to get to reconstruct your original problem. So the reconstruction might not necessarily be addition. So for Fibonacci, we just added the two numbers together, but it won't necessarily just be addition. It could be a whole bunch of possibly very complex statements. So this is the strategy for solving DP problems, and almost every single DP problem will require you to do these steps. So before we actually go through the steps, I'll just talk about when we should use DP, or when would be, what sort of scenarios would be helpful to think about using DP. Of course, there's no definitive rule that says if I see this, you must use this particular technique, because with programming contests, you sort of never know. And if they change the question slightly, a particular technique might not work. But just as a sort of overall guide, we can try thinking about using dynamic programming when grading, the greedy algorithm, or other techniques doesn't seem to work. So with greedy, you should try to sort of not think about using the greedy algorithm if you can, because a lot of the time the greedy algorithm won't work. So unless you can sort of convince yourself or prove to yourself that the greedy algorithm will work, try not to use grading. Also, you should think about using DP when it's easy to count the smaller cases, but when you try to scale that sort of same technique to the larger cases, it becomes increasingly complex to break that down. You can also think about using dynamic programming if you're being asked to find an optimal solution. So if you want to find a solution that is as large as possible or is as small as possible, you can think about using DP. Also, if you want to count the number of solutions. So if you want to calculate the total number of possible unique solutions, you can use dynamic programming as well. So these are sort of the classic sort of statements you'll see in the questions where you're using DP. And when we know we're going to be using DP, these are the sort of steps I like to go through to make sure I've covered all the ground before I actually start any of the coding. And once you've got all these 4 down and you've convinced yourself that your algorithm will work, then coding it up should be pretty easy, because it just translates to converting this into your C++ code. So the first thing you need to do is you need to define your state and your subproblem. So I think this might make a bit more sense when we actually go through the questions, because I think if you haven't done DP before, this like states and subproblems won't make much sense. But you're going to need to define a state. So each subproblem is going to rely on a state. That state could involve 1 or more variables, and then you're going to have a subproblem based upon that state. So you could say, if I'm in this particular state, what is the possible number of solutions up until this state? Or what is the optimal solution given the state up until this particular sort of number? So that's your subproblem. And then the next thing you're going to do is you're going to identify your base cases. So just like with the Fibonacci sequence, with every single recursion, you're going to keep breaking it down into smaller and smaller and smaller subproblems, but eventually you'll get to your smallest subproblem, your base case, where you can't break it down any further. So in this case here would be just your 0th and first Fibonacci number, in which case you can't break it down any further. So this would be normally the subproblem where you have only, for example, if you have 1 element, or if the 2 variables are equal, for example. So those are your base cases. And then you're going to write down a recurrence that links your base cases together. So you're going to need to identify your dependencies. So other than your base cases, all of the other subproblems will depend on other subproblems. So you'll need to work out which subproblems will need to be used to solve your bigger subproblem. And then you also need to think about an ordering as well. So you'll need to order your subproblems so that, for example, you'll be finding your base cases first, and then you'll be finding the next subproblems which directly use your base case, and then so on. And then you also need to work out what's the original problem. So the original problem could just be a particular subproblem for the whole entire list, or for the original value of n, or it could be, for example, to find the maximum number or the minimum number out of all your subproblems, for example. So these are the sort of 4 steps that you'll need to write down just in English, plain English, before you actually start coding. So again, if this doesn't make much sense to you now, because let's say if you haven't done DP before in like 3121, then this will make a lot more sense when I actually go through the problems. So in Comp 3121, you would learn, these classic dynamic programming problems. I'm not going to go through these because they're pretty well known, and you can just Google these in your own time, as well as their variations. But I think it's worth learning these because the sort of patterns or the sort of questions you will be doing in dynamic programming, you can sort of borrow these ideas, or borrow the idea of the recursion or the subproblems when you're doing the problems. Okay, so now we're going to actually go through some actual contest level, sort of easier level questions. So this is one-dimensional DP. I'll talk about what one dimension versus 2 dimensions mean later. So this question says, determine the number of binary strings of length n that does not have 3 consecutive zeros. So a binary string, how do I draw? So a binary string just means a string containing zeros and ones. So I could have 0, 1, 0, 0, 0, 1, 1, 1, 0. And this has a length of n. So in this case here, we've got 5, 6, 7, 8, 9. So n is equal to 9. So this is a binary string of length 9. And we don't want there to be any 3 consecutive zeros. So in this here, I've got 3 consecutive zeros, so this won't count. So a valid binary string would be something like 0, 1, 0, 0, 1, 1, 1, 1, 0. So that also has n is equal to 9 numbers, and there's no 3 consecutive zeros. Okay, and of course, if you have 4 consecutive zeros, that won't count as well, because there'll be 3 consecutive zeros here, and then there'll also be 3 consecutive zeros here. So you can't have 3 or more zeros. So how could we possibly think about trying to count the number of binary strings of length n? So this seems like, I guess, a high school perms and comms question, right? So you've got n items in a row, yeah. So you can order these in n factorial ways, and then you've got how many zeros, how many ones. So then you've got to divide it by the amount of zeros factorial, divided by the number of ones factorial. Okay, but then I guess this comes your first problem. You don't know ahead of time how many zeros and ones you're using. So then I guess you could try doing cases, yeah. So you could think about doing cases where you've got, for example, 1 0 and then n minus 1 ones, and then 2 zeros and then n minus 2 ones. But then that becomes too hard. And then how do you consider, removing these 3 consecutive zeros? So you would have to subtract the cases where you have 3 or more consecutive zeros, and then count the complement. And then it becomes a bit too hard, because you've got all of these ideas simultaneously that you're trying to solve, and then you can't really combine this together. Okay, so yeah, so this seems like a high school maths combinatorics problem if you've done perms and comms in 3-year maths or 4-year maths. But then putting this all together becomes way too hard. Okay, so directly counting, all right, when we have n numbers is too hard. So then I'm thinking, well, if I can't directly count n numbers, the next thing I would probably try to do is just to try small cases and see if I can find some sort of pattern. So if we have n is equal to 1, then we just have 2 strings, yes? So namely 0 and 1. Yeah, so 2. And if you have n is equal to 2, then that would be 2 squared. 2 squared, yeah? So you can have 0, 1, 0, 0, 1, 0, and 1, 1. So just, so each of your 2 spots can be either 0, 1 or 0 and 1. And then for n is equal to 3, we can apply the same idea. So this will be 2 cubed. So each of the 3 slots can have a 0, 1, or 0, 1, or 0, 1. But then we need to subtract the case where we have 3 consecutive zeros, which will be 0, 0, 0. So we have all the binary strings of length 3, which is 2 cubed. Then we subtract the binary string 0, 0, 0. So we have this sort of pattern now. So, so we have 2, 4, and then we have 7. So now if we go for n is equal to 4, how can we do this? So we've got 1, 2, 3, 4 slots. And then if you try doing this, you sort of realize it becomes a bit hard, right? Because sort of directly counting the number of ways you can get 3 or more consecutive zeros, you'll end up just basically brute forcing it. So the idea of dynamic programming is we want to try and use our solutions, our known solutions for our subproblems, to try and fill in the rest. So what do I mean by that? So let's say our binary string of length 4 ends in a 1. Okay. So if the binary string ends in a 1, that means we can fill the rest of these. We can fill out these 3 numbers in any way we want, really, because this one here doesn't really restrict what happens over here, because all we care is that there is no 3 consecutive zeros. So if there's a 1 here, then this won't affect the number of consecutive zeros afterwards, right? So then I just need to count how many ways are there of putting the zeros and ones in a length of 3 with no restrictions. So the answer would just be 7, right? So I can fill this in 7 ways, because through direct counting, I know that if I have n is equal to 3, I can add this in 7 ways. So if the last number is a 1, there are 7 ways of filling that in. How else could we end this? Okay, we could have this ending in a 0 and a 1, right? So we can have the last 2 ending in a 0 and 1. And then with the remaining 2, with the remaining 2 slots, I can fill this in 4 ways, right? So we've got 2 slots here, and I can fill that in n is equal to 2, which is 4 ways. So if we end in a 1, 0, then I can fill this in 4 ways. And similarly, if I end in a 1, 0, 0, then I just have 1 spot left, and then I have 2 ways to fill that in. So this idea is sort of the basis of how we're going to be. How do I clear my drawings? So that sort of idea there of trying to break down or trying to construct longer sequences from our already known solutions of smaller sequences is what dynamic programming is about. So what if we consider small cases? So I've got 2, 4, and so that's 2 cubed minus 1, which is 7 ways. For n is equal to 1, 2, and 3. And then we can use our existing solutions to construct solutions for higher values of n, as I've just shown you. And that's the main idea of DP. So we're going to go through all of our steps now. So these steps here. So these steps here to actually solve this in DP. So first of all, we're going to need to define our state and our subproblem. So our states will be the length of the string so far. So if I've got a binary string of length n, that's going to be our state. And we're going to let our subproblem be Cn is the number of binary strings that have exactly n digits. So if this here is a binary string of length n, we can count this in Cn ways. So we'll say that this is Cn. So then the next one is our base cases. So we've already found this through direct counting. So C1 is equal to 2, C2 is equal to 4, and C3 is equal to 7, which we've just found directly. And then the last, or the next step is we want to find which subproblem will answer our original problem. So that would just be finding Cn. So we want to find a formula for Cn. And then we want to try and find a recursion that allows us to find Cn in terms of the smaller terms. And then eventually we can continue to break it down into smaller subproblems until we end up with just our base cases, which we can sub in. So this is our recurrence then. So for n greater than or equal to 4, a string with n digits, so that's our state, can end in a 1, 1, 0, or 1, 0, 0. So just to sort of convince yourself, if I end in a, if my last two digits were, like, for example, 0, 1, okay, so if I have 0, 1 instead, then the last digit would be 0 anyway, so that would be counted over here, right? So that's why I don't have, for example, 0, 0, 1 or 0, 1, 0, because these are already counted as part of these cases here. So you should convince yourself that all of your strings must end in either a 1, 1, 0, or 1, 0, 0. And you can't have, for example, 0, 0, 0, because then you would have 3 consecutive zeros. So with each of these 3 cases, we can count then using using our known subproblems how many ways. So if in the first case, when the string ends in a 1, okay, so if we have a string that ends in a 1, then the remaining string with length n minus 1 is also going to be a valid binary string, right? So then I can just count C n minus 1 ways, and then that would give me all the total number of strings, binary strings, which end in a 1. Okay, so the number of strings that end in a 1 with exactly n digits is equal to C n minus 1. And then we can apply the same idea with if the string ends in a 1, 0. So if the string ends in a 1, 0, then we have n minus 2 numbers left over to fill in. And this must also be a valid binary string. So we can have any valid binary string here because there's no restriction on the number of zeros. And then this would just be Cn minus 2 ways. Okay, so if we end in a 1, 0, then there's Cn minus 2 ways. And then if we end in a 1, 0, 0, same idea. So if we end in a 1, 0, 0, then we have n minus 3 numbers left over. And this is also going to be a valid binary string. And we can fill this in Cn minus 3 ways. So if we add up all these cases, we just get Cn is equal to Cn minus 1 plus Cn minus 2 plus Cn minus 3. And this here becomes the recursion, the recurrence. And now, if we want to implement this in code, we've got all the tools now. We've got our recurrence, we've got our base cases, and then once we solve our recurrences, we just need to solve the original problem. So we just need to print out what Cn is. So when we actually implement the code, we should think about the order, right? We need to think about a good evaluation order. Otherwise, it's will be really bad if we try to find Cn, which requires Cn minus 1, Cn minus 2, Cn minus 3. But if we haven't found these, then we will just be adding on their uninitialized or default values. So if you're using, for example, arrays, and these are initially set to 0 because that's the default behavior for arrays in C and C++, then yeah, it would be pretty tragic if you try to evaluate subsequent terms without actually finding your previous terms. So because this recurrence is fairly simple, we can just evaluate in order of n. Yeah, so we can find C1, C2, C3, C4, C5, and so on, because each subsequent term only depends on the previous 3 terms. So this is what the code will look like. So if we implement this in C, then we can just construct an array called D, and we can initialize D1 is equal to 2, D2 is equal to 4, D3 is equal to 7. So those are our base cases. And then we can find D4, D5, D6, and so on until we reach Dn by just adding the previous 3 terms in our array. So di is equal to di minus 1 plus di minus 2 plus di minus 3. And this is guaranteed that when we use D1, di minus 1, di minus 2, di minus 3, we've already found them. Okay, so we don't need to worry about having these uninitialized, because since we're doing this in order, these would already be found. And then to answer the original problem, we should have written here printf. Let me try text. Yeah, we should also answer the original question. So printf %d new line d n. Okay, so we should add something like that in as well. So that just answers the original problem. So this is what we call a bottom-up DP, because we're starting with our base cases, and then we're going to next find the states which directly need your base cases, so D4. Then after we find D4, we find the next available possible state, so D5. So we're going from the bottom up. We're starting with our base cases, and then we're working our way up towards N. There is another style of programming of DP, which is called top-down, and we'll look at another example later on. So there's another recurrence which exists, which is Cn is equal to 2 Cn minus 1 minus Cn minus 4. As an exercise, you can work out yourself why this works. So this solution takes O(n) time, because we've got a for loop with n terms, and O(n) memory, because we need an array that carries n objects. There is a trick, a nice trick that you can reduce this, that allows you to reduce this down to O(1) memory by recognizing that with your DP, you only need your previous 3 terms. So if I want to find C200, I only need 199, 198, 197. So all the other terms before that become irrelevant now. So we can just sort of use this nice trick with moduluses to use constant space. So then you only need an array of length 3. Yeah. Also, what happens if n is huge? This is just an aside as well, which we won't cover. But if n is really, really huge and we don't want to solve this in O(n) time, then it is also possible to solve this in log n time using matrices and fast exponentiation. So you can research this in your own time if you want. All right, so in the previous problem, each state's depended on one parameter only, and we call this a one-dimensional problem. So our state is just Cn, and that just depends on the length of the string. So we don't have to restrict ourselves to just one variable for our states. We can have 2 variables or more variables. Yeah, you can basically have as much variables as you want. Just be careful, if you have too many variables, then it just means your occurrences will be a bit harder. So this next problem, this is from the Australian Informatics Olympiad. So if you want to actually code this up yourself, you can submit it on ORAC. I'll just open up this version because there's a bit more space. Yeah, you can read, if you want, you can read this in your own time. There's a lot of reading, and yeah, with programming contests, yeah, there's a lot of reading, and a key part is just is solving problems fast, right? Which means you want to try and skim over the that's spelt wrong. You want to try and skim over the unnecessary details and just focus on what is this question actually asking us to do. So once you have a read of this, this is pretty much the summary. Pretty much, you've got a shopping center with n floors, and you're currently over here on the ground floor, on the left. and you want to reach the 3rd floor or the nth floor, the very top floor on the right side. And you have a bunch of elevators which can go left or right. And you also have the ground traveling across the floor. And you want to try and find the fastest way. So the elevators all have different speeds, and they all have different speeds, and you can also run across the ground with different times as well. And that's all given to you. So given the times it takes you to traverse all these elevators and stuff, you want to try and find the optimum way. So for example, there's no numbers here, but let's say the optimum way might look something like this, for example. Okay, so that will be let's say, for example, the fastest way. And this question just asks you to output in, I think, seconds, the number of seconds which is most optimal. So the first thing you could probably try thinking of is a greedy algorithm. So for example, you can try choosing the fastest possible elevator at each point. So for example, if I'm over here, there's 2 possible paths I can choose, and then I can pick the fastest elevator. And then over here, I can choose another 2 possible, I can run across here, or I can go up here, and then I can choose the fastest along there. But yeah, you'll realize that this won't work. So for example, if the first elevator you choose was really quick, and then every subsequent elevator you hit after took too long. And then there's a whole bunch of other sort of greedy ideas, but none of them sort of work. But the main observation you need to make is you can either end up on the left or right side for each floor. So that means in your state, in your DP state, you'll need to consider on both sides, both left and right sides, the fastest possible time, which is what I've written over here. Yep. So to answer the questions now, so remember the sort of 4 steps that we had before. So what is your state? So in this question here, we've actually got 2 parameters in our state. So we have the current floor that we are on, so ground floor, 1st floor, 2nd floor, as well as whether we are on the right side or the left side. So this would be your 2 parameters. So what floor and whether you're on the left or right. So what is the subproblem then? So you're trying to assign a value to your state now. So if we are on a particular floor and we are on the left or the right side, then we'll call that value the minimum time it takes to achieve that floor on that side. So we'll say, or we'll call the function to be dp f comma s, where dp is the array or function storing your value, f is the floor you're on, and then s is just either L or R, depending on whether you're on the right side or the left side. So then what about your base cases? So the base cases would just be the times it takes for you to run on the ground floor. So on the ground floor, on the left side, that would just be 0. Yeah, so the minimum time is 0 because you're already there. And then on this side, on the right side, the minimum time would just be the time it takes for you to run across the floor, because there's no other way to get there. Okay, and then those are our 2 base cases. So dp1l is equal to 0, and then dp1 right is equal to floor on floor 1, so the time it takes to run across level 1. And then we need to answer the original problem. So the original problem would be to reach the nth floor on the right side. So that would be dp n comma right. So what is the recurrence between the subproblems now? So the recurrence is if we want to find the minimum time it takes to reach the ith floor on the left side, then we can achieve this from sort of 2 possible ways from the previous floor, right? So either I could start on the left side, and then I can come up to this side. For example, going this way and this way, or I can go like this, sort of this way, and then, sorry, you can start from this side and then come up that way, or you can start from this side here and then come up via this way. So that's what we've got over here. So we can either start from the I-1 floor on the right side, and then travel on the right elevator, so like this way, or we can travel from the I-1 floor on the left side over here, and then come up on the elevator and then come via the floor on the I level. And then the right side will just be the same, but just the reverse way around. So if I want to come onto the right side, I can come from the previous floor from the left side and then come up via the left elevator, which is that, or I can come via the right elevator and then go through the floor. So I can start on the right side, come through the right elevator and then come through the floor. So this is your recurrence then. So then implementing this in code would be fairly straightforward then, because now you've got your base cases, which you can write out, and then you can just subsequently find for each next level, so first floor, second floor, third floor, the two values there. So the other thing I want to mention is what about our order? Okay, so in this case here, if we're going from floor to floor, from first floor to second floor to third floor, then that's completely fine because we maintain our order, because the ith floor only depends on the I-1 floor. So as long as we work our way up the floors, we should be fine. So we'll code this up now. Since we're sort of short on time, I'll just try to quickly code this up. So I'm not going to actually write code which you can actually submit because we're going to miss the sort of input and output, but I'll just try to translate our pseudocode into C code. So we need to have our input and output. So I'm just going to write left, right, and floor as our arrays. So we'll just have int, we've got n left, and I think there's, I think from memory there was 100,000 as our constraints. Yeah, 100,000. And then same thing with right and floor. So you'll just, you have some sort of input and output to store the values into here. And then for our actual DP, the first thing we have is our base cases. Yeah. So that means we also need to store our DP. So we'll create an array as well for our DP. It is in 2 dimensions. So our first dimension will be the number of floors that we have, which is 1,000. Okay, so I'll chuck 1,001 here, and we've also got 2 here. Okay, so this 2 corresponds to whether we're on the left or right, and we'll just use zeros and ones to represent left and right. So then we'll need our base cases. So our base case is first floor on the right is equal to 1, and then we've also got our first floor on the left is 0. Now, because this is initialized to 0 anyway, you technically don't need this because it's initialized to 0, but I'll just write this out so that it's clear what the initial values are. So that's our base case. And, oh, sorry, that shouldn't be a 1. That should be floor 1. So, yep, so those are our base cases. Then we need to construct our subproblems. So we'll use a for loop to go from level 2 to level n. So for int I is equal to 2, we're going to go to the next level, which is 2, and we'll stop once we hit. I just realized I don't have syntax highlighting. Sorry. So this is our for loop, and that goes from floor 2 until we reach floor n. And since and this is fine because we're going in order anyway. And then this is our recurrence. So you can pretty much, I think you can pretty much just copy this and just make some fixes. So dp I L, instead of using L, we're going to use 0, and this is equal to min. Now we need the algorithm header as well. So hash include algorithm for min. dp is lowercase dp. That's I minus 1. R is the index of 1. Right I minus 1. And that was easy. And that's dp I minus 1. L we used 0. And then that's left I minus 1 plus floor I. Okay, so that's the left side done. And then the right side would be basically the same. Okay, so I'll just copy that. So all these R's become 1. L becomes a 0. That becomes an array instead of a function, and that becomes lowercase. That becomes lowercase, and instead of being a function, this is an array. Okay, so that should pretty much do it. Okay, so this for loop will calculate, that should be brackets as well. I should turn on syntax hiding as well. That's a bit better. Yep, so this will calculate dp on the ith level for left and right, for the left and right sides. And then lastly, we need to answer the original question, which was just to print out dp on the nth level on the right side. So this corresponds to that. So we can see that the hardest part isn't necessarily the programming, the coding, because the actual implementation is pretty straightforward. The hardest part probably is working out what states you want to use and working out what is the recurrence between your subproblems. So again, in this question here, what we've done was a bottom-up implementation. So we're starting off with our base cases, and then we're working our way up towards our original problem, which was n. Now, in the next problem, we're going to be doing top down DP. Do you have time for that, Angus? Or
yep, it should be fine.
Yeah, yeah, we've got around 15 minutes. So we'll do one more problem, and then we will we'll go through the problems. So this is Mortal Kombat Tower, which is from Code Forces. So you and your friend take turn fighting end bosses, and they can be easy or hard. At each turn, the current player can kill 1 or 2 bosses, and your friend is not good enough to kill the hard bosses, but your friend can use 1 skip point to kill 1 hard boss. And you want to determine the minimum number of skip points needed to kill all the end bosses in the given order. So the inputs will be the number n, which is the number of bosses, and then you have an array of length n, where it's binary encoded. So the value is 0 if the boss is easy, and 1 if the boss is hard. And you wanted to find the number of skip points that you need to use. So here's the example. So the example input is n is equal to 8. And then the next line contains n integers, which are 0s and 1s. So the first boss is hard, the second boss is easy, the next 2 bosses are hard, next boss is easy, and then the last 3 bosses are hard. And you and your friend take turns trying to kill these bosses, and you can kill 1 or 2 at each point, and you can't skip. Okay, so your friend goes first. So since your friend, so this is the optimal game plan, and you just got to trust me, I guess. So your friend can kill the first 2 bosses. So your friend, draw. Your friend will kill these 2, and since this boss is hard, you use 1 skip point. Okay, so you're using 1, and then in the second round, it's my turn then, and then I can kill the 3rd and 4th bosses, so I can kill these 2. But since I'm better than my friend, I don't need to use skip points, so that's fine. Then my friend can kill the 5th boss, and since this is easy, no skip points are used. And then the next round, I kill the 6th and 7th bosses, and since it's me, I don't need to use any skip points. And then the last round is my friend's turn, and my friend will just kill the last boss using 1 skip point because my friend is not good enough to kill the hard bosses himself. So in total, you're using 2 skip points, and you just need to trust that this is the most optimum way. So this is what we call a decision-making problem, because at each sort of next step, you need to decide whether you're killing 1 boss or 2 bosses. And that's pretty much the only decision you make, yeah, because you don't get to choose the order that you're playing in, because it's always your friend starting first, then it's your turn, then your friend's turn, then your turn. So the only thing which matters in terms of the decision making is whether you kill 1 or 2 bosses, and that becomes the decision you need to make. The other sort of thing you need to notice is, let's say we pick an arbitrary boss. Yeah, so let's say I choose like this guy here. We don't know ahead of time whether I'm going to be the one killing this boss or your friend is going to be the one killing this boss. So we actually need to work out for both cases what happens if it is my turn for that particular boss. So that becomes our 2-dimensional DP, because our state will be the current turn, the current position that we're on. So how many bosses we've sort of killed so far, or how many bosses we need to kill left, as well as whose turn it is. So this is a decision-making problem where at each step the player has to choose whether to kill 1 or 2 bosses, and we don't know ahead of time which player will kill a given boss. So that means when we do our DP recurrence, we need to consider both players killing each boss. So each boss will have to be killed by both players on that turn. So the DP value that we're going to be using, we want to calculate the number of skip points used so far. And remember, the number of skip points used is the number of hard bosses that your friends kill. Okay, so not including the ones which I kill myself, only my friend. And we want to minimize this value. So recall that we can use DP, or we should think about using DP when you want to try and find an optimal solution. So if you want to find minimum or maximum of something. And this question as well, the superphone question, was also a optimization problem, because we wanted to find the minimum time. And we found the minimum time by calculating the minimum time at each possible state. So again, in this Mortal Kombat Tower question, we are also minimizing skip points. So for each player, we need to consider what happens if they kill 1 or 2 bosses, and then we can choose the optimum. So that means we want to choose the minimum amount of skip points used out of that. So let's try to work out what our state, subproblems, and so on are. So our state depends on where we are at the moment, so what round we are on, which boss we are trying to kill at the moment, as well as whose turn it is. Right? So, yeah. So the index of the boss we are fighting and the person whose turn it is, and then we're going to let the subproblem be the minimum number of skip points at this particular state. So if I've got n bosses, so 1, 2, 3, 4, 5. So let's just say these are our n bosses. If it is this boss we're trying to kill, then we can consider or we want to consider what is the minimum number of skip points needed to kill from here onwards if the current player is oh, that's wrong. Sorry, no, that's right. I circled the wrong thing. If we're currently the player P. So if I'm killing this guy, or if my friend is killing this guy. So that's our subproblem. The original problem would be to solve this for the whole entire boss, all of the bosses. So that would be the 0th boss, starting with my friend. So we'll say my friend is, your friend is player 0, and we'll use 1 for myself. So what are our base cases then? So our base cases would be if we only had 1 or 2 bosses, one boss, right? So if it's my turn, then I can kill either 1 or 2 bosses, regardless of if they are hard or even. And this would be optimum because if it's my turn, then I can just kill as many bosses as I need because I don't need to use any skip points. So I might as well just kill them, and no skip points are needed. So if I have 1 or 2 bosses left, regardless of whether they are hard or even, then I can kill them without incurring any, without spending any skip points. If it is my friend's turn, however, then if there are 2 bosses left, then it might be better for me to sort of hand it over to my friend instead. So then in this case, the base case here would be if you only had 1 boss left, because that would mean you're forced to kill that boss, because you remember you can't skip turns and you can't just send it to your friend. So you're forced to kill the last boss, regardless of whether they are hard or even. So then the value for your base case for your friend's turn would just be the value of whether the last boss is easy or hard. So what's about your recurrence then? So we've solved our base cases and our subproblem. So what about our base cases? So let me just clear our drawings. Okay, so if we have these players here, if it is my turn, okay, so let's say it is my turn and I kill this boss, then I can kill, remember, in the previous slide, I mentioned that the decision becomes I can kill either 1 boss or 2 bosses, right? So what we'll do is we'll consider the 2 cases and then we'll just choose the best scenario out of that. So if it's my turn, I can kill 1 boss and then hand over the rest to my friend. Or I can kill 2 bosses, regardless of whether they are hard or easy, and then hand over this rest to my friend. And then it just, the number of skip points used is unaffected, because since it is currently my turn, then I don't need to use any skip points. So I just consider the minimum value out of the DP starting from here, as well as from here. So in other words, if I'm currently at state I, then I just consider DP from if I'm at I plus 1 and I plus 2 onwards, and then I just take the minimum number of skip points used from that. So over here, that's what I've written. So if it is currently my turn, I can either kill 1 or 2 bosses, and then next turn will be my friend's. And no skip points are used, so I don't need to add on the values. So in terms of the equations, if I'm at position X, then if I'm at position X and it's my turn, then I just consider what happens if I kill 1 boss. So I'm at position X plus 1 now, and it's currently my friend's turn. Or I can kill 2 bosses, so then it's currently X plus 2, position X plus 2, and it is also my friend's turn. And then I take the minimum out of those. Okay. Alternatively, if it is my friend's turn, right? So let's say I'm at position X. So it's currently position X now. My friend can also kill 1 boss. So I can kill this guy. And then I just consider the DP from X plus 1 onwards. However, since my friend is the one killing the boss, the number of skip points used depends on whether the current boss here is easy or hard. So if this value is 1, the boss is hard, so I just add on 1 to the number of skip points used over here. And if this boss is easy, which is 0, then I just leave the number of skip points unaffected. So we'll just use the trick where the problem says that the difficulty of this boss is called AX. So remember that AI is the 0 or 1, depending on whether the boss is hard. So we're just going to add on the value of this to dp of x plus 1, which is what we've got over here. So AX plus dp, then we're starting at position x plus 1. So we've killed one boss, and then it becomes my turn again. So I'm player 1. Or we can also kill 2 bosses, right? So the other thing we could do is we can also kill the next boss as well. And then we consider what happens with x plus 2 onwards. Okay, so the number of skip points used at x plus 2 onwards. And then it depends on how many hard bosses are over here. So that would just be the value of AX plus 1. So we just count how many hard bosses are over here. So that's the recursion. So that should be capital DP. So DP x0 is equal to the minimum out of these 2 scenarios. So we can either kill 1 boss or we could kill 2 bosses with adding on the necessary skip points that I've used. So now, now we're going to implement this. Again, since we're running short on time, I'm not going to actually implement this sort of properly. So the code might be a bit buggy, but we'll just see how we go. Okay, we're going to implement this top down now. So that means we're going to do this recursively using our recursive function, because even though it is possible to do this iteratively, because we can predict ahead of time the necessary order, I just want to demonstrate this sort of process. So normally with DP, we're going to construct a function. So we'll call this function DP. That takes in our state. So we said our state here was x comma p. Okay, so the index of the boss we're currently fighting and the person p whose turn it is. So x comma p. And we're going to have to return something. Okay. In our main function, so int main, our job is to print a single value, which was the original problem. So that original problem here was dp00. So that's what we're trying to find. And then this is the only sort of time where we directly invoke this function. And then every other sort of calling of this function dp will be done recursively. So the next thing we're going to do is we'll do our base cases. So if it is my turn, okay, and there are 1 or 2 bosses left, then I can just kill them and no skip points are needed. So that would be 0. Okay, so if it is my turn, so p is equal to 1, and there are 1 or 2 bosses left. So if there are n bosses altogether, then we're looking at position. Oops, I just went LaTeX mode for a moment. X is greater than or equal to n minus 2. Then we can just return 0. Okay. Whereas if it is my friend's turn, so if p is equal to 0, whoops, that's ampersand, and x greater than or equal to n minus 1. So that would be there's 1 boss left. Then they are forced to kill this boss. So if they are forced to kill this boss, it depends on whether this last boss is easy or hard. So that value is a n, a n minus 1. Okay, so the last boss is at position a n minus 1. Okay, it's because I'm using it. I'll just make it I'll just make it 1 base. Now I'll just stick with 0 based because I think everything else is 0 based. Sorry. Yeah. So whatever this is, whether you're using 1 based indices or 0 based indices is up to you. I'm just going to use 0 based indices because that's what I'm used to. So we've got our base cases then. So we've got 2 base cases depending on whether whether it's my turn or the player's turn. So for our recurrence now, okay, this is our recurrence. And again, you have 2 cases depending on whether it's my turn or your friend's turn. So if it is my turn, so if P is equal to 1, then you want to return the minimum out of these 2. So we want to return the minimum out of dp x plus 1, comma 0, or dp of x plus 2, comma 0. Okay, so this would mean it's the next term would be my friends, and I've killed 1 or 2 bosses. And I don't need to add on the values for dp to dp because if it is my turn, I'm unaffected. Okay, and then else it is my friend's turn. So we don't need if statement here because we've got sort of early returns. My friend's turn. So then I just return this. Okay, so the minimum out of ax plus dp, x plus 1, comma 1. So ax plus dp, x plus 1, comma 1, and ax plus a, x plus 1. So this, remember, is the number of hard bosses that you're trying to kill. And then that is 2 because you're killing 2 bosses. Okay, so this is pretty much it for the DP function. Now, as it stands, if you try to run this, it will probably work, but it would be very, very slow. And the reason for this is because you're going to be accessing the same states multiple times. So as a part of the implementation, you want to also cache your values. Okay, so that means I will create a array called cache, and this has 200k possible values. So we're gonna use a an array called cache, and then we'll store the scene values. So if we come across the scene value, we can just pull it out of the cache rather than trying to recalculate it. So, okay. So to implement this cache, we just need to be careful with what we initialize the values of our cache to, because if we just leave it uninitialized with all zeros as default, and we try to say if cache x p return cache x p. If you just try to do that, remember that the DP values could be 0. Yes, so the cache, or yeah, the DP values could be 0. So we can't just check whether this contains a non-zero value because the values could be 0. So what we'll do is I'll just initialize all the values to like a nonsense number like -1, because -1 can never be achieved. And then we know that if we get a non-negative -1 answer, then we've seen it before. I guess the other way you could do this is you could create another array called scene and then have this to be 0s and 1s as well. It's up to you. Okay. That also means I need to initialize all these values. Yeah. So I should also initialize cache with all -1 values. And you could do that using a for loop, or you could also use std fill from the standard library. So, okay, so this is our cache. So if we see the value in our cache, we're going to return it. The other thing that we need to remember is we need to store the value into our cache after we found it. So the way I'll do that is I'll just return cache is equal to that, cache is equal to that, case is equal to that, and case is equal to that. So that should work because in C++ or C, when we return this value, it will assign the value, whatever this value is, to this, and then it will return that value as well. So I think this code should be able to run if we fix up the input and output, but I'll probably just stop there in the interest of time. Yeah, but yeah, with input and output, that's just a bunch of for loops. Oops, wrong problem. That's just going to be a bunch of inputs and outputs, which stores in N and stores in N and A. Okay, so that's pretty much what I've written down here. The other thing I wanted to mention is with recursion versus iteration, it just depends on what you want. There are, benefits and disadvantages of both techniques. If you do top-down, which is recursion, it's very natural for you to implement that because implementing the code is basically directly translating your recurrence, right? And it computes the subproblems only as it's needed. So you only ever call this function if it is needed. So this is good when you have a lot of unreachable states because it will not visit these states. However, the downside of recursive is there will be sort of a lot of overhead in the function calling, and you have like a sort of like in the memory you have like a sort of stack of the functions being called. So where memory optimizations are needed, iterative would be generally be better. However, you need to be careful with the ordering, or with the ordering. Yeah, so bottom up would be could be faster if you get the ordering right. Just be careful you order it. You visit the states in a correct order. The last thing is just, you can read this in your own time, but I've just put down sort of some general DP patterns, and you should sort of learn these and their variations. Of course, the sort of pseudocode here won't be exactly the same as all your questions, but this just covers some sort of possible ideas you could use for your states and your recurrences. But yeah, with all the questions, the states and recurrences are always different. But yeah, hopefully this would sort of help you with determining your states, because yeah, working out a good state which will work is probably one of the hardest parts of DP. So what I'll do is I'll hand over to Angus now, who will run the remainder of this workshop.
Thanks. Yes, I'll start by stopping the recording.